Hello everyone, picking back up with the start of week 11 notes on page 101 in your workbooks. Today we're going to be digging into a whole brand new type of function called exponential functions. Before we start going deep into that, what I'd like to do is review real quick what we've done so far in this course. So we've looked at two different types of functions so far specifically. Linear functions, which was in that standard format of y equals mx plus b. Hopefully that looks a little bit familiar to you guys. But the biggest thing I want you to recognize here is that it just has one x in it, technically x to the first. The fact that it has an x to the first is what makes it a linear function. Then we moved on to quadratics, which is what we did most recently. Notice that one has an x squared in it. A lot of times you'll see the x squared and an x to the first, but the whole idea of it being a quadratic is the fact that it has an x squared in it. So there's different methods of solving, different types of graphs that you get out of these two types of functions, and now we're digging into a whole new one. So an exponential function. To know that something is an exponential function, you're going to see something like this, where x is in the exponent. That's what makes it exponential. It kind of sounds weird to remember it this way, but exponential has an x in the exponent. A lot of x's going on. So the second you see this, think about your x, and it's up in the exponent. Okay? So that's really all you need to know about exponential functions for now. What we're going to start doing today is going over some rules of exponents, some that you already know, and digging a little bit deeper into some other ones that we might not be too familiar with, or that we haven't seen in a while or maybe ever, and then we'll get into what methods we need to know for solving exponential equations. Okay, so some background knowledge that will help us while we're working through this is knowing perfect squares, which we did go over with factoring. Remember, perfect squares are the results that you get when you multiply any number by itself. So starting with 1 times 1 is 1. So that means 1 is a perfect square. 2 times 2 is 4, so that means 4 is a perfect square. So you can pause the video now, or at least just try to come up with them on your own. 3 times 3 is going to be 9, and the list just goes on like that. And you can stop at 100. It does go on. I'm not really going to give you numbers quite bigger than that you'd have to work with. You want to be able to recognize these numbers. So what I mean by that is if you have an exponential equation and it's got a 25 in it, you should know that it's 5 squared, or it's 5 times 5. If you see a 48, you should think that's not a perfect square. Okay, perfect cubes are a little bit different. It's the same idea, but because it's perfect cubes, it's the result of a number multiplied by itself 3 times. So for example, in the parentheses, there is 2 times 2 times 2. I'm going to start off with 1. 1 times 1 times 1 is still 1. Okay, 2 times 2 times 2 is 8. Keep going with this list. Okay, try 3 times 3 times 3. Remember, you don't really need to go too big with your numbers. I won't give you that many. Perfect cubes are a little bit harder to recognize because you don't really work with them too much, or you probably haven't worked with them too much. But 1, 8, 3 times 3 is 27, 3 times 3 times 3 is 27, 4 times 4 times 4 is 64, and 5 times 5 times 5 is 125. And then the list goes on, 6 times 6 times 6, and so on. Okay? So those are perfect squares and perfect cubes. Now we're going to dig into some exponent rules. Exponent rules we know a lot of already because we've done some exercises with them. We just haven't really applied a rule we haven't actually gone over the exact rule yet. So when you're multiplying two terms together, the rule is that you add your exponents. So I want you to write on the line x to the a plus b, and then just simply write add exponents. Now for each one of these, we're going to do an example that might help it make a little bit more sense to you. But if you're multiplying two terms with the same basis together, notice these are both x's, you add the exponents together. So for example, let's say I have x squared times x, something you've definitely seen before in the past. Now keep in mind, this is actually x to the first, so when I multiply them together, it's going to be x to the third. Something that I used as a reference for you up to this point, rather than saying add your exponents, is just count how many you have total. X squared is xx, and then times another x, you're going to have 3 total, so x to the third. Okay, for multiplication, you have to add your exponents. So for division, you are going to subtract them. Your rule is going to be x to the a minus b. Okay, subtract exponents. So an example of that, I'll give you x to the 5th divided by x to the 3rd. The way that we had done this previously is, let's say you have 5 x's on top and 3 on the bottom. 3 are going to cancel and leave you with 2. It's the same idea, we're just putting a rule to it now. 5 minus 3 is 2. So whichever way you want to look at it, both are effective. This rule might simplify it a little bit so you don't have to draw so many x's or think about it in that light. Just remember to subtract. Whether you're a rule person or a concept person is completely up to you how you understand it. Right, here are some new ones that we're getting into now. So a power to a power really just means an exponent to another exponent. Notice the a and the b are both up here in the they're both up there as an exponent. It looks like there's parentheses between them, which generally means multiplication. If that helps you to remember the rule, you're going to multiply your exponents together. So this is going to be x to the a times b, or in other words, you multiply your exponents. Okay, so for an example, for exponent to exponent, or a power to a power, let's use those same numbers. I'll do x to the 5th cubed. Okay, so x to the 5th cubed, I multiply my exponents together and I get x to the 15th. If you want to see the reasoning for why that is, if you have something to the 3rd power, we already talked about that a little bit earlier in the notes, it's multiplying that thing by itself 3 times. So this is x to the 5th times x to the 5th times x to the 5th. When you're multiplying, you add your exponents together. So this is really x to the 5 plus 5 plus 5, or x to the 15th anyway. So that's just a more complicated way of looking at it, or just a reason for why you have to multiply your exponents together. It's because that's happening that many times. All right, the next one is the easiest rule, but the one that a lot of people forget because it's so simple. Anything to the 0 power is always going to be 1. Okay, so for example, 7 to the 0 power is 1. Okay, another example, actually we'll get into that in a second. Don't worry about that. We'll get there. Okay, anything to the 0 power is 1. Okay, after the easiest rule is probably the most difficult rule to remember, a negative exponent. So when you're using exponent rules, you are never allowed to leave a negative exponent. So you have to apply this rule anytime you see a negative exponent in a problem. So the rule, I'm just going to write it out for you first and then we'll talk about it, is 1 over x to the positive a. Okay, 1 over x to the positive a. So when you have a negative exponent, what you're going to do is flip your fraction. And I want you to underline fraction. We'll talk about that in a second too. Flip your fraction and make exponent positive. Okay, flip fraction and make your exponent positive. Right, so you might be looking at it and thinking that what we originally had, x to the negative a, is not a fraction. Kind of like what we had to do with slope. You need to turn it into a fraction by putting it over a 1. So anytime you have a negative exponent and you've got to apply this negative exponent rule, you turn it into a fraction first. So x to the negative a over 1. Then you flip it, so notice the 1 went on top, the x to the negative a went on the bottom, and then you make your exponent positive. So that's why it's raised to the positive a. So for an example, let's do x to the negative third. Technically, it's not a fraction, so I'm going to make it one by putting it over a 1, and then I flip them. So the 1 moves to the top, the x to the negative third moves to the bottom, but I make that 3 positive. So it's kind of nice that it's the same rule every time. When you see a negative exponent, that's the process you go through. All right, these next two aren't rules, but they're so important for applying these exponent rules. So a little note, everything in the parentheses is being raised to the exponent on the outside. So when you see an exponent on the outside of the parentheses and more than one thing inside of the parentheses, all of it on the inside is being raised to that exponent. So this right here, xy to the a, notice the x and the y are both in the parentheses. So this is actually x to the a and y to the a. They're both being raised to it. Before even looking at that next line, look underneath it at this little star on the bottom. If you see x, then parentheses y to the a, notice only the y is in the parentheses, so that means only the y is being raised to the a. The x is not. Okay, so it's all about where your parentheses fall to see what's being raised to the certain exponent. So this one over here, x over y to the a, the x and the y are both in parentheses, so they're both being raised to the a. This is x to the a over y to the a. All right, so keep that page handy for you. We're going to go through and apply these exponent rules. Okay, so the biggest thing that people struggle with exponent rules is knowing when to stop. It's kind of like that idea of factoring completely. You keep going until nothing else applies. So when we were factoring, you would take out a GCF first, and then if you could do trinomial after that, you would. You would just keep going if you could. Same thing goes with exponent rules. If you multiply and then you can divide after that, and you have a power to a power, you keep applying all of those rules until you can't anymore. How do you know when each one applies? You look at the operation that's happening. So for 343, it's x to the 8th divided by x squared. That tells me I'm going to use my division rule. What do you do with exponents? When you divide, you subtract them. So this is going to be x to the 8 minus 2, which is just x to the 6th. All right, adding a little bit to division, for 344, I have coefficients or numbers in front of my variables now. Those are still being divided. So the rules that we just went over on the front page are about the exponents. These numbers in front have nothing to do with subtracting your exponents. You still divide those like you normally would. 12 divided by 6 is 2. Then you do x to the 12th divided by x to the 6th, where you note that you subtract your exponents. So 12 minus 6 is going to be x to the 6th. Notice the big difference between when you're dividing coefficients and what you do with your exponents. They're exponent rules. So when you were told to subtract them, you only subtract your exponents. Okay, backing away from division for a little bit. For 345, the two terms are being multiplied. Think about what you're supposed to do with exponents when you're multiplying two terms together. You add them. So 3 plus 6 will get me x to the 9th. Next one, using the same numbers, but different rules. So I have x to the 3rd raised to the 6th. This is exponent to an exponent. They're both up there as a power. Think about what you're supposed to do. What rule did we go over? When you have power to a power, you multiply your two exponents together. So this is x to the 18th. It's all about memorizing those rules and then practicing applying them. The next one, jumping back to division. Remember what we said in the very beginning. All of these rules apply when you have common bases or common variables. I can't do x to the 6th divided by y squared because which letter would I bring down? It doesn't make sense. You have to keep common letters together. So I can still divide this piece by piece. I'm going to do x to the 6th divided by x to the 1st. Remember what you do with your exponents when you're dividing? You subtract them. So 6 minus 1 is going to be x to the 5th. Do the same thing with your y's. Y to the third divided by y squared. 3 minus 2 is 1. So I'm just going to write it as y, but you could write it as y to the first. That would be correct as well. All right, for 348, there is no there's no operation technically happening in 348. To figure out what rule applies, think about all the rules we have. This one has a negative exponent, so this one's going to use that negative exponent rule. So the first thing you have to do when you see a negative exponent is make it into a fraction. So I'm going to put it over a 1. And then after that, what you need to do is flip the fraction 1 over x to the positive 4. You flip them and you make the exponent positive. All right, next one has a lot of multiplying. So 349, there's negative 3x squared y times 5x to the 7th y cubed. So multiply common things together. When you're multiplying, we know that our exponent rule is to add our exponents together, but that has nothing to do with these coefficients, the numbers. Those aren't exponents. You multiply them like you normally would. That's going to get me negative 15. Now I applied the exponent rules. X squared times x to the 7th. I add those exponents together and I get x to the 9th. And then y to the 1st times y to the 3rd. 1 plus 3 is y to the 4th. This next one's not really a rule, but just something to really make sure you understand what's being raised to the 3rd power here, the x or the y. Trick question, both. They're both in the parentheses, so the x is being cubed and the y is being cubed. And that's it. It's not really a rule, it's just something you really need to make sure you understand, especially for this next question. So for 351, what is being raised to the 3rd power? 2x squared is all inside of the parentheses. So the 2 is being raised to the 3rd power and the x squared is being raised to the 3rd power. Honestly, I think this is the toughest example on this page. And as you can see, those last few examples get pretty tough. So the 2 is being raised to the 3rd power. Think to yourself, what is 2 to the 3rd power? 2 times 2 times 2 is 8. Now we have x squared to the 3rd power. That's a power to a power rule, which means I have to multiply my exponents together. X squared cubed is going to be x to the 2 times 3, which is 6. So I'm going to go over that one again because it is rather tricky. Okay. Everything in the parentheses is being cubed. There are 2 pieces inside of the parentheses. There is a 2. That's what's being cubed first. So 2 to the 3rd power gets me 8. Then I have x squared in the parentheses, so it's also being cubed. X squared cubed is looking like this. I have x squared to the 3rd power. They're both next to each other like that. It means you multiply them together using your power to a power rule. 2 times 3 is 6. This next one might actually help piece that together a little bit more as well. 3 and the x squared are both inside of the parentheses, so that means they're both being squared on the outside. So this 3 is being squared. That's going to get me 9. This x squared is raised to the 2nd power, a power to a power rule. Again, I know you can't really see it because they're not next to each other, but it is an exponent to another exponent. When you see it like that, you're going to get x to the 2 times 2, which is 4. All right, let's move on up here to the top, 353. So this one, again, it's kind of not technically a rule. It's just knowing what's raised to the 4th power. The x and the y are both in the parentheses, so they're both being raised to the 4th. I get x to the 4th, y to the 4th. All right, these next 3 or 4 examples are pretty tricky, okay? 354. Everything in the parentheses is being raised to the negative 2nd power. I have to use my negative exponent rule. So I first start by turning this into a fraction by putting it over a 1. Then what I'm going to do is flip it, so 1 over 3x, but I make that a positive 2. This one's tricky because it's the first example we've had so far where we're actually not done because I can simplify this further. On the bottom, this is set up a lot like 351. where I have two things inside of the parentheses and they're both raised to an exponent. Whoopsie. Oh my gosh. On the outside. Okay, so the 3 inside of the parentheses is being raised to the second power, and so is the x being raised to the second power. So the 1 stays because that's not in the parentheses. On the bottom, the 3 squared is going to get me 9, and then this is like x to the first being squared. When I multiply those together, 1 times 2 gets me x squared. Now there's nothing else I can do. No other rule applies. There's no parentheses to work with. I know I'm done. Now this next one kind of looks like the same problem, but there's no parentheses there. So what that tells me is that the only thing raised to the negative second power is the x that's attached to it. The 3 is not raised to the negative second power in this case. So the 3 just carries over. It has nothing to do with the exponent rule we're about to apply. Okay, now when I apply that negative exponent rule to the x, first remember you need it to be a fraction, so I'm going to put it over a 1. And then I'm going to flip it, so it's going to become 1 over x to the positive 2. You can leave your answer like that, or you can multiply it out. When you multiply fractions, you multiply straight across, so it would be 3 on top over x squared. But either one of those answers is perfectly fine. But see the difference between 354 and 355 and what's being raised to the exponent. All right, moving right along, some zero exponent rules. So for 356, 12 to the 0 power, try to think of what it is. I'll give you a second. Anything to the 0 power is 1. Done. However, for 357, I know the rule is everything raised to the 0 power is 1, but look at what's being raised to the 0 power in 357. The whole thing is not being raised to the 0 power, just the x is, because there is no parentheses there. So just like that one we did 2 examples ago where the 3 wasn't part of it, I just bring the 3 over. And then x to the 0 power is 1. So your overall answer for this one is 3. I'm going to throw in a little extra example for this one. If I had 3x in parentheses to the 0 power, that means everything is being raised to the 0. So the 3 and the 0 all raised to the x power, that would be equal to 1. But because the 3 was not raised to the 0 power over here, it's not part of the 0 power rule and it just carries over. Big difference between all of these 3 examples. And remember what we talked about in the beginning. You keep applying an exponent rule until you can't apply another rule anymore. So these next few examples, you're definitely going to be going through a few different rules throughout the whole process. So for 358, I start with division. X squared divided by x to the 5th. When I'm dividing variables, I subtract my exponents. So this is 2 minus 5. It's always going to be top minus bottom. That gets me -3, so I end up with x to the -3rd. And I know that I'm not done at this point because I can apply my negative exponent rule. So now I'm going to go ahead and apply my negative exponent rule. So I start by turning it into a fraction. Then my negative exponent rule is to flip my fraction. So it becomes 1 over x, and I make that 3 positive. All right, next one's got a lot going on to it, but it's actually only one step, so hang in with me. All right, try to think to yourself, what's being raised to this 3rd power on the outside? Okay, if you were thinking everything, your answer is correct. Everything is in the parentheses for this one, so that means everything's being raised to the 3rd power. So that means the -2 is being raised to the 3rd power. The x squared, the y to the 5th, the 3, and the z to the 3rd. Is all being cubed. So first, -2 to the 3rd power. -2 times -2 is 4, times -2 is -8. X squared to the 3rd power is a power to a power rule, so I multiply them, I get x to the 6th. And then y to the 5th raised to the 3rd, again power to a power rule. I multiply those together and I get y to the 15th. In the denominator, same idea. 3 is being raised to the third power. 3 times 3 is 9 times 3 is 27. So I get 27 in the denominator. And then the last thing is z cubed. So I have, just to write it out so you guys can kind of see what I mean, power to a power rule. It's being cubed, then it's being cubed again. When you have power to a power, you multiply them, you get, z to the 9th. Now, I know I already gave it away. I said there's only one step here. We did that one step. We applied that, everything being raised to the third power. At this point, you'd want to see if another rule applies. It looks like you should be able to divide, but you can't divide because there's no common variables. You have x and y on top and a z on the bottom, so there's no variables to divide, and 8 doesn't divide by 27. It doesn't even simplify nicely, so there's literally nothing else you can do to this. That's your final answer. Right, the next one has negative exponents. You are not going to apply your negative exponent rule quite yet, because if you start flipping these, here's what a lot of people try to do. You get 1 over x squared over 1 over x to the 6th. Who wants a fraction over a fraction? That's like 3 fractions in 1. It's disgusting. Okay, so here's what you're going to want to try and do instead. Here, let me get rid of this too. Boop. Use your division rules, and then we'll simplify after. So you can divide your x's. When you divide, you subtract your exponents. Now this one is a little bit tricky. When you're subtracting these exponents, you have -2 minus your bottom exponent, which is a -6. You're subtracting a negative here, and we know that that becomes positive. So when you subtract those two exponents, you actually get 4. So I have x to the +4. Which looks a lot easier than what I just wrote when I tried to use my negative exponent rules first. Now I move on to the y's. Y to the 4th divided by y to the 1st. Y to the 4th divided by y to the 1st. When I subtract my exponents, gets me y to the 3rd. And that's it. I can't multiply those together because they're not common variables. There's no other rules that apply. This next one's definitely a challenge question. Think about what's being raised to the second power here. There's separate parentheses on top and bottom, so you have to take that into consideration. On the top, x to the -3rd is being squared, and y to the -4th is being squared. And again, it's power to a power rule, so I multiply. X to the -3rd squared is going to get me x to the -6, and y to the -4th squared is going to get me y to the -8th. On the bottom, think about what's being raised to the -4th power. X to the 1st and y to the 3rd are both being raised to that exponent. Again, it's power to a power, so you multiply. This first one is x to the 1st raised to the -4th. 1 times -4 is just -4. And then y to the 3rd, whoops, what on earth? Y to the 3rd raised to the -4th. Again, power to a power. 3 times -4 gets me y to the -12. Now think to yourself, are you done? Is there anything else that can be applied? The answer to that is yes. There's division that can happen here. They're all negative exponents, but for the same reason as the last question, you don't want this to turn into 1 over x to the 6th over 1 over x to the 4th, 1 over blah, blah, blah. It just gets disgusting. It's technically not wrong, but it's not as simplified as you can be. You want to try and do your negative exponent as your last step because it is the ugliest one. So because we can divide, I separate my variables, x's and y's. First, x to the -6 divided by x to the -4. Remember, you have a -6 minus, because we're dividing, you subtract your exponents, a -4. This one's going to become that same rule where you add them together. -6 plus 4 is a -2, so I get x to the -2nd power. And then with y's, there's -8 minus the bottom exponent, which is -12. Again, you have a double negative there, so it becomes addition. -8 plus 12 is going to get you 4, a +4. So that'll be y to the 4th. Are we done? Nope. We have a negative exponent here. Last step is to get rid of that negative exponent. Y to the fourth has nothing to do with that, so that's going to carry over in the answer. So x to the negative second, I turn it into a fraction so that I can apply my negative exponent rule. I flip it so it becomes 1 over x squared, and like we said, the y to the fourth just comes down. So you can leave your answer like that, or like we did before, you can multiply straight across and you'll get y to the fourth on top over x squared. Both of those answers are perfectly fine. Whichever one looks more normal to you or makes the most sense. All right, one more example. If you're feeling up for it, I'd actually love to see you guys try that one on your own. So pause it for a second. I'm just going to jump right into it. So there's separate rules for the top and the bottom. You can't start dividing quite yet because you have two different x's on top. Which one divides by the x on the bottom? You can't do it yet. So you have to simplify the top first and then simplify the bottom. Then we can get into the division. So on top I have multiplication. When you multiply two variables together, you add your exponent. So I get x to the 7th on top. On the bottom, think about what rule applies. I have x to the 5th raised to the 2nd power. So that's a power to a power, which means I multiply them together. I get x to the 10th. So far I've used two different rules, and I'm still not done. Now I have division. When you divide variables, you subtract the exponents. So 7 minus 10 gets me a negative 3. I know I'm not done because, again, I have another rule that applies, my fourth rule for this problem now, a negative exponent. So I am going to apply my negative exponent rule by first turning that into a fraction and then flipping it. So when I flip this, it becomes 1 over x to the positive 3rd. Nothing else applies to this, so that is your final answer. Okay, so again, you apply your exponent rules until none of them apply anymore. Sometimes you're only going to have to worry about doing one rule. Like a lot of the examples on the left side of this page, sometimes they're going to be a little bit more difficult, like the last few examples we did. But practice makes perfect. If you know those exponent rules, you should be able to apply them, okay? Over and over again. Just like if you knew how to factor, you were able to apply those factoring methods over and over again. So what we're going to do now is get a little bit away from those exponent rules and get into learning methods for solving exponential equations. But before we do that, real quick, your code word for today's video is going to be water. And your code word is water. Apparently I'm thirsty. All right, so remember what it means to be an exponential equation. We stemmed away from that for a second, but think about what we talked about in the very beginning of today's lesson. To be an exponential equation means there's an x in the exponent. Okay, so exponential equation means that there is an x in the exponent. There are two different methods that you can use to solve an exponential equation, just like the different methods we learned for solving a quadratic. So big review, real quick for quadratics. Quadratics could be solved by factoring and then teeing it up, and then they could also be solved by using the quadratic formula. If you remember, which hopefully you do, the quadratic formula works all the time. Factoring and teeing it up only works when you have something that's factorable. This is kind of that same idea. So this common basis method that we're about to start going over right now only applies if you can find common bases. And we'll talk about what that means in just a second. But this method does not always work. Okay, this method does not always work, only when it can. Some people prefer to learn the two different methods because this is arguably an easier method than the one we're about to do. But again, it doesn't always work. Okay, here's how this method works. So here's the how-to. I'm going to walk you through it through an example. So your directions are just to solve for x. I see it's an exponential equation because look at where your x is. It's up there in the exponent, which means it's an exponential function, which tells you this method applies. What you want to do is get these numbers that I'm circling right now to be the same. Once they're the same, and this one already is the same, which is very nice, you get rid of them like they were never there. And you bring down your exponents. So x equals 3x minus 4. The reason this is necessary is because when x is up in the exponent like that, you can't solve it until you bring it down. So this method of common bases, getting these two numbers to be identical to each other, ends up bringing them down. Once you do that, you just solve for x like you would solve any equation. Get your x's all to one side, and then just try and get the x by itself. So for this one, I'm going to subtract 3x over to the left side to get my x's together. 1x minus 3x is a negative 2x, and that's equal to negative 4. Now my last step to get x by itself is to divide by negative 2, divide by negative 2, and I get x is equal to 2. Now, I'm really only going to show you this once, but you can check every single equation every time, no matter what kind of equation you have, as long as you plug that x back in to your original everywhere you see an x. So my original equation was 3 to the x equals 3 to the 3x minus 4. I'm going to plug in a 2 everywhere I see an x. So 3 squared equals 3 raised to the 3 times 2 minus 4. Well, 3 squared on the left is 9. On the right side, I'm going to simplify that exponent first. 3 times 2 is 6 minus 4 is 2. You might already see it. 9 equals 9. It checks out. All of these can be checked using that method. Just take your answer, plug it back in, make sure it works. All right, now going back to this common basis method that we started talking about for this first example. Notice I circled those numbers in the beginning. They were both already 3. That's not usually going to be the case. So for 364, notice one of my bases is 5 and one of them is 25. Okay, we talked about this in the very, very beginning with knowing your perfect squares and your perfect cubes. You want to be able to manipulate one or both of these bases to make them common or make them the same. So what I mean by that, and just kind of watch for this one. 5 to the x is great. I can rewrite 25 without changing the value of it at all to be 5 squared. 5 squared is 25, so notice I didn't change anything. I just rewrote it so that if you notice right here, at 5 and 5, oh my goodness, 5 and 5, common bases, those will just cross right out and you bring down your exponents, x equals 2, that's your final answer. It's done. You can check this one too, probably very quick mentally. Just plug in 2 right here. 5 squared does equal 25. Checks will work every time. Okay, now if you like this method, remember it doesn't always work, but it's definitely the faster method if it does apply. So 365. Again, I don't have common bases, but it's very similar to 364 that we just did with that whole idea of 25. However, it's in the bottom. Think about what type of exponent will bring that to the denominator of a fraction. That would be a negative exponent. Okay, so the way that this is going to be written using common bases, I still want my base to be 5, but it's going to be 5 to the negative second power, because if you think about what we did on the whole last page with exponent rules, 5 to the negative second, if I wanted to convert that, I'd put it over a 1, and then I'd flip it. 1 over 5 squared would get me the 1 over 25. So that's why that negative exponent rule comes in handy when you're working with these common basis examples. Okay, so these 5s cancel each other out. Boom, you're already done. X equals negative 2. Okay, practicing a couple more. So 366, 3 to the x minus 2 equals 27. You can't turn 3 into 27 by raising it to a power. So what you have to do is bring down 3 and know that 3 is going to be your base. 3 to what power will get you 27 is really the question you're asking yourself. It's going to be 3 to the third power. And now that I have my common bases, those cross out and I bring down my exponents. X minus 2 equals 3. To get the x by itself, I add that 2 to both sides, and I get x equals 5. Now you might be liking these so far. The last few examples that we've done were pretty typical, easy examples. We're going to get into some tougher ones now. So this bottom one right here, 1 over 27 and 9. Take a second to try and think about what base you'd want to use. For all the last examples, we really just took the smaller of the two and made that work. The smaller of the two for this one is 9. 9 to some power will never equal 27. It is impossible. It's not going to work out. So you need an even smaller base for this one. So think about a number that could be raised to any exponents that could get you 27 or 9. It's going to be 3. So if you're really not understanding common bases, just stick with me for this last example. I don't think I'm going to do too many more. And then I'm going to show you the other method that works all the time. You need to know the other method anyway because it works when common bases doesn't. So it's really like the go-to method, but some people prefer common bases if it's applicable. So for 27, if I need to write 27 with a base of 3, notice the 27's in the denominator, which tells me right away it's got to be a negative exponent. And 3 to the third power is 27. Now, that's just rewriting this piece right here. I have to bring down the rest of this exponent because it's still part of the problem. I'm going to bring it down as 3x plus 1 next to that negative 3 that goes along with my 1 over 27. I know this is equal to, I have to also write that 9 using a base of 3. 9 with a base of 3 is going to be 3 squared. And then same idea, I still have to bring down the exponent that's already there, 2x plus 5. I have common bases, so those are completely gone, and I can bring down my exponents. So negative 3 times 3x plus 1 equals 2 times 2x plus 5. Hopefully we're seeing we've got the distributive property for this one, so I'm going to distribute on both sides to start. So negative 3x times 3x is a negative 9x, and negative 3 times a positive 3 is a minus 3. I bring down that equal sign. 2 times 2x is 4x, and 2 times 5 is a plus 10. All right, keep using your solving equations rules to get this to be an x equals to get your final answer. Hopefully what you're noticing right now is you do have two x's in this equation and they're on opposite sides. So I always move the smaller, but it's up to you, whichever one you decide to move. I'm going to add the 9x to both sides. So that gets me negative 3 equals 13x plus 10. Now to get my x by itself, I get rid of what's being added or subtracted first. So I subtract that 10 that's being added to the other side. Negative 3 minus 10 is a negative 13. That equals 13x. And then I divide both sides by 13, and I get x equals negative 1, which I could absolutely plug back in and check. If you like this method, practice with those last 4 examples. I'm not going to get too much into these ones because, like I said, you need to know the other method regardless, and it's usually the fan favorite for solving exponential equations. So what I mean by this common basis method won't always work. For example, 372 on the next page. If you try to rewrite 500 with a base of 7, it is not going to work. If you try, let's do like 7 to the third power. I don't know, we're guessing because we don't know. That gets me 343. Then you try 7 to the fourth power because you're optimistic, but 7 to the fourth power is equal to 2,401. So there is no exponent that you can put on 7. Sorry, no whole number exponent that you could put on 7 and rewrite 500 using. So common bases doesn't work. When common bases doesn't work, you need an alternative method. This is like the quadratic formula of the exponential functions. It's the method that always works, but absolutely must be used when common bases can't work. So you can use this all the time, but you must know it even if you like common bases better. That's usually why it's a fan favorite. People like to learn one method. All right, so again, here's the how-to. We're only going to do a couple of examples today, and then we'll pick up with this in the next video. But I just want you to see this other method while we're kind of comparing the two right now. So the directions are to solve for x and round to the nearest tenth. Here's the method. It's called logs. And you're definitely going to need your calculator for this. So pause it real quick if you do not have your calculator with you. Go ahead and grab it. The method's really not too bad once you get the hang of how the method works. So your first step when solving is to look, well, first check to make sure it's an exponential equation. There's an x in the exponent in this first example, so that tells me that I can use logs. So here's how you use the log method. You start by simply writing the word log in front of both sides of your equation. You don't know what log is right now, and you don't need to. You're gonna start by writing the word log on both sides. Notice the 7x comes down and the 500 comes down. All I did was add the word log. Now, log is actually an operation. It's something that can just be done on the calculator, but its purpose is to make this not an exponential equation anymore. It takes your variable that's up in the exponent and it brings it down. I tell people when I'm teaching this all the time, logs chop down the x. Think about chopping down a log. You use logs to chop down that x and bring it down in front. So that x moves to the front of log 7 and everything else just comes down. Again, you probably still have no idea what I'm talking about with logs. That's okay. As long as you understand how the process works, you're golden. Okay, now that I don't have x in the exponent anymore, x is solvable and it's right here. So I just need to get it by itself. Just like I'd solve any equation, you're trying to get x alone. Right now, x is being multiplied by log 7. So to get rid of log 7, we are going to do the opposite and divide by log 7. So notice what happens. Log 7 divided by log 7, even though you don't know what that is. You know, anything divided by itself cancels. Then the x comes down, and here's where you might be thinking, oh no. You are going to plug this right here into your calculator. So that's why you need your calculator. Hopefully you have it right now. There is a button on your calculator that says log. The log button is directly next to the 7. I think it's right to the left of it. So you're going to press log. Walk this through with me. Press log and it'll give you an open parentheses. You're going to type in 500 and then you're going to close your parentheses. I cannot stress that enough. So far you've typed in log 500 and then you closed your parentheses. Type in divided by, hit the word log again. It opens up parentheses for you. Hit 7 and then close your parentheses again. And press enter. This is the decimal that you should be seeing on your calculator. Again, yours might be a little bit longer. Remember, my calculator rounds a little early. As long as you have those first few decimal places, you're good to go. If you're not getting that, practice plugging it in your calculator again. And if you're still not getting it, please send me an email or come to office hours, okay? But I was told in the directions to round to the nearest 10th, so I'm at my final step. I just need to go to the nearest 10th, which is this place right here. But I look at the digit after it, 5 or above, give it a shove. So this is going to become 3.2 as my final answer. Now, that was the first log example you've probably ever done. Some of you may have worked with them before, but it's definitely the first log example you've done for this class. Doing the process over and over again is what makes it such a fan favorite because it's honestly the same thing every time. So moving on to 374. Do the exact same first step we did for the last example. You start by just writing the word log in front of both sides of your equation because still the same rule applies. What you do to one side, you do to the other. The purpose of the word log is to take that exponent and bring it down in front so that it's no longer an x in the exponent. So that x over 3, even though it's got a little more to it this time, same process, it comes down in front of the log of 2, and then the log of 52 comes down. Now look at what we did in the last example at this step. You're trying to get x by itself. Now that it's out of the exponent, it's solvable. I get rid of my log now that it's served its purpose. It's already done what it needed to do. It brought that x down in front, so now I can get rid of it. X over 3 is being multiplied by the log of 2, so I'm going to divide both sides by the log of 2. Over here, the log of 2 divided by log of 2 cancels because anything divided by itself cancels, and the x over 3 comes down. Now I plug this in my calculator just like we did before. Remember, it's going to give you an open parentheses. Make sure you close it, then divide it by open parentheses and close that as well. So take a second to practice plugging that in your calculator. I'm going to write down the decimal that I get when I plug it in, and you can just double check with mine once you're there. Again, yours will be a little bit longer. Mine just rounded a little early. Okay, hopefully we got that decimal. If you're having a hard time plugging it in your calculator, please reach out to me some way. Okay, x is being divided by 3 right now. I'm almost done. I almost have my x by itself. I have to undo that divided by 3 by doing the opposite and multiplying both sides by 3. So this left side, the 3 and 3 will cancel, leaving me with x. My equals comes down, and then in my calculator, I just take that decimal I just got and multiply it by 3. So I should get 17.101319, which when rounded to the nearest tenth, that 0 definitely doesn't bump that up. It stays 17.1. And that is where we are going to stop this first video. Again, remember to write down that code word if you didn't already, and get practicing on the homework assignment if you want to get a little bit ahead. And